To evaluate the quality of an op-amp design, we need some metrics that we can use. This video is going to discuss a bunch of metrics that are relevant to op-amps. And I meant it when I said a bunch, so buckle up. We'll talk more about how to calculate these parameters on the next slide. On this slide, I'm just getting a bunch of definitions out of the way. These parameters can be roughly split into new parameters for op-amps and parameters we've seen before. But the parameters we've seen before often have some mild twist in the op-amp context. We'll start with new parameters for op-amps. One really common question when you see an op-amp schematic is which input is inverting. We denote that by adding the V plus and V minus symbols to the appropriate terminals such that the output increases when V plus increases. Another crucial measure of the amplifier is how much gain does it have. I've referred to that here as the open loop voltage gain instead of just saying gain for reasons that will be clarified in future videos. The gain is multiplied by the differential input in order to produce the output. Since gain is a small signal parameter, we may well go through the other really relevant small signal parameter now, which is the small signal differential input impedance. This parameter is important because it's how we meet the infinite input impedance specification for an op-amp. However, it might be surprising that this is a small signal measure at first glance. You might say, don't we sometimes put big voltages into an op-amp? And we do. But because op-amps are always used in feedback, and because feedback acts to minimize the difference between V plus and V minus, the inputs only ever see a small differential signal. And consequently, RNDM is an okay measure of the impedance that an input will see, even though there are some subtleties with how the impedance is affected by feedback, and technically the inputs aren't purely differential. The input bias current, input offset voltage, input common mode range, power supply rejection ratio, and common mode rejection ratio are all parameters that ought to be familiar from differential amplifiers. There are a few little spins on these that we care about in the context of op-amps. The input offset voltage is a small signal, but in most of our amplifiers in this course, we've sort of conflated the idea of being a small signal and being a signal that exists in an amplifier's midband. So most of our small signals have been AC. Offsets are a small DC signal, which is relevant because op-amps don't have a midband. They work all the way down to DC. The input common mode range is a super important specification on op-amps because the input differential mode range is always kept small by feedback. So as our input moves around, the common mode of our signal moves around with it. So we don't care a ton about the input differential mode range of an op-amp. We do care a lot about the input common mode range. And one especially important common mode range to try to achieve is called a rail-to-rail input common mode range, or rail-to-rail operation. That is a design specification that says that the input is allowed to reach all the way up to VCC and all the way down to negative VCC on an op-amp, so it can touch either the positive or the negative rail. CMRR and PSRR are important for op-amps, just like they are for any differential circuit. PSRR is nice to have because you never really want your power supply noise coupling into your output, but CMRR is absolutely essential to the operation of an op-amp because, again, it's used in feedback, so the common mode moves around a lot, and if you can't reject the common mode, then this differential functionality of the op-amp breaks down. Finally, we see another couple of familiar specifications. The output swing is familiar from every amplifier we've looked at, and it matters for the same reasons as before. It determines what signals your op-amp can provide. The dominant pole location is crucial for op-amp operation because it's related to op-amp stability. We'll talk more about stability later, but for now we want to note that calculating the dominant pole is important, and we can usually do so by finding the open circuit time constant of the compensation capacitor. Finally, there's a new op-amp schematic specification called the slew rate that's fancy enough to warrant its own video. So we'll see that in the next one. Now that we've gone over a list of parameters, let's see how to calculate them from a schematic. Most are pretty easy to find just by looking at the transistors, which is cool. Sorting out which terminal is positive and which is negative starts by perturbing one of the input terminals upwards. We follow that effect to the output node of the differential stage, and we see that perturbing the left input upwards results in the output going upwards. Because more current is steered to the left, that would drop this node and raise this node. Raising this node causes our gain stage output to decrease because the gain stage is inverting. Our level shift makes an exact copy of that decrease. And our output stage is also non-inverting, so it copies the output of the level shift. So we see that raising the left input causes the output to go up, causes the output to go down, which means that it's the inverting input. Note that I trace the signals through in terms of voltages here, but you can also think about currents running around the amplifier as well if that's easier to propagate. The key simplification to keep in mind when we're finding the input polarity is that you're only looking for a direction of a relationship between these perturbations. So you don't need to calculate exact gains, just think about whether a node will move up or down. We find gain in the same way we always have. The differential stage is a single-ended differential actively loaded diff amp, so its gain is GMRO over 2. Interstage loading is given by a divider between the diff stage output resistance of RO over 2 and the gain stage's input resistance of beta RE. And finally, the gain stage resistance is RO over RE. The level shift and the output stage both have a gain of 1 and a fairly high input impedance, so I'm not modeling them here. Similarly, our differential input resistance is given by small signal parameters of our first stage, and it's 2R pi in this case. The input bias current is given by the input device's collector current divided by beta. And that recipe is going to be the general approach to finding input bias current. Take a collector current divided by beta. In this case, the collector current is given by the tail current over 2 because it splits evenly between these sides. But you'll need to examine your op-amp carefully to find what current is running in your input device. The input common mode range is limited by a VO max and a VO min. VO min is VBE on plus VCE set. And that expression comes from the VBE on of the input device and the VCE set of the tail device. VO max is VCC minus VBE on minus VCE set plus VBE on. And that expression comes from VBE on in the mirror, VCE set of the input device, and VBE on of the input device. The output swing looks like it might just be limited by VCE set of the devices in the output stage at first glance. But finding the output swing in amplifiers where multiple stages have a gain of 1 can be kind of tricky. In this case, the swing is limited by the front half of the class AB amplifier. So in order to achieve this VCE set swing, this node would have to swing above the voltage rail because it would be a VBE on above the output. And that means that this stage provides our limiter, and we can figure out what its limit looks like by taking a VCE sat drop across this device and then a VBE on drop to the output. Or on the bottom side, taking a VCE sat increase across this device and a VBE on to the output. So remember, when you're analyzing output swing, especially in op amps where there's only one gain stage, you need to be careful that you're not limited by a previous stage. Finally, our dominant pole is given by the open circuit time constant of the compensation capacitor. So you find the OCTC for this, and that'll tell you where your pole is. That's because the compensation capacitor is deliberately large and deliberately in the Miller position, so we can assume its time constant is going to be way bigger than any other capacitor in the circuit. Because this compensation cap is in a Miller position, wrapped around a common emitter, we can often assume that its OCTC is going to be given by a left-right pattern, where we find the resistance to ground from the left node and the resistance to ground from the right node in order to quickly calculate the OCTC. In this case, the left plate is going to see RO over 2 from the differential to single-ended stage to ground, and beta RE from the gain stage to ground, so the parallel combination of those two values. And the right plate is going to see RO of the active load and 1 over GM from the emitter follower. So in summary, op amps have lots of parameters, but we've seen a bunch of them before. You can find the input polarity by perturbing one input and then propagating the direction of that change through to the output. And other parameters come from typical analyses, often with active loads. You need to bear in mind that you can be limited in your swing by the behavior of a prior stage, so you don't just look at the output to find your output swing, and that the dominant pole almost always comes from the compensation cap.